Hello everyone, welcome to Probability and Statistics for Data Science. In previous videos, we have talked a lot about linear models for regression. Today, we're going to explain how to use linear models to perform classification. The resulting method, which is called logistic regression, is extremely popular. It's used all over the place in data science. Let's get to it. We're going to talk about logistic regression. Just to remind you about the difference between regression and classification, in regression, we want to estimate a quantity which we call the response, which is typically continuous. Here it's the premature age-adjusted mortality in US counties. We want to estimate this quantity from several features. Here the features are smoking and household income. In classification, instead, we have a number of predefined classes. So in this example, which we will discuss in more detail later on, there are two classes, which are healthy and having Alzheimer's disease. And our task is to assign these classes to data points based on multiple features. So just as in regression, we have several features. Here we have two features, which are the volume of the entorhinal cortex and the volume of the hippocampus. And in our data, we see the class assigned to different values of the features. So here, this patient has a hippocampus which has a volume of about 0.27 and an entorhinal cortex which has a volume of 0.1, and they have Alzheimer's, as indicated by the black dot. Our goal is for a new patient, for example here, that has a certain value of hippocampus volume and a certain value of entorhinal cortex, we want to determine which class we should assign to this patient. The data typically look like this. There's a vector of features and a label that indicates what class is assigned to that specific vector of features. We encode the features typically as a d-dimensional vector, and the label, again, which is yi, where I goes from 1 to n, indicates what class is assigned to those features. In our example, the features are two brain volumes extracted from an MRI scan, but they could also be the actual values in the voxels or the pixels of an MRI scan or another medical image. And the class is the status of the patient. Do they have Alzheimer's disease or are they healthy? Our goal, again, is to assign one of these predefined classes to new data. The way we do this, you will probably not be very surprised about it, is through probabilistic modeling. So we model the features as a random vector x, realize that now the x has a squiggly line on top because it's a random vector. It's not a deterministic vector with fixed values. We model it as a random vector that has uncertain values and is associated with a certain distribution. And the labels, we also model them probabilistically. That's why there's a squiggly line on that y. Now this y is a random variable that is going to have a PMF. It's obviously a discrete variable because there's a discrete number of predefined classes. Now, if we encounter a new data vector x, and this is a fixed vector because it's just the values we have observed in one particular instance for each of the features, a very reasonable way to assign the class is to say, okay, if we have the conditional PMF of y given x, which tells us the conditional probability of each of the classes given every possible value of the features, then we can just see which class is more likely if we condition on the specific values that we have observed. And that's a very reasonable thing to do, and in fact it minimizes the probability of making an error. So this makes it sound like classification is easy. We can just take our training set, and for every possible value of x, we see how many examples belong to each class, and we compute the empirical conditional probability of each of the classes given that specific value of x. Now, when we encounter a new data point, we can just look at those probabilities and decide which class is more likely. So this makes it sound as if classification is super easy. Is that the case? Maybe think about it for a couple of seconds? The answer is that it's not easy at all, and this is because of the curse of dimensionality. So we have a whole video on the curse of dimensionality, but let me remind you what the problem is. The problem is that unless the number of features, which are the entries in this random vector x, is very small, it is going to be absolutely impossible to estimate every possible conditional distribution of the labels, given the features. In other words, we are not going to be able to compute all the possible conditional PMFs because the conditional PMFs are going to be different for different values of x, and there are just too many. To drive this important point home, imagine that the features are binary, and the features often are continuous, which makes it even more difficult, right? The volumes that we saw a moment ago are just continuous values. But let's imagine that the features can only have two values, say 0 or 1. Then how many conditional PMFs do we have to estimate if there are m features? The possible values of x are 2 to the m. This means that we have to compute, that looks a little bit weird, are 2 to the m. My iPencil decided to go a little bit bananas. That means that there's an enormous number of possible conditional PMFs that we would have to estimate from the training set. If m is 100, which is by no means a large number, there's many applications where you want to use up to 1,000 features, but definitely many where you want to use at least 100. 2 to the 100 is completely insane. We would never have that amount of data. So it's going to be highly likely that when we encounter new examples, they will have values of x that are unique, for which we have seen no other values that have exactly that configuration in the training set, so we won't have been able to estimate these conditional PMFs. And that's why classification is difficult. We need to make assumptions so we can actually fit our classification model to data and estimate these conditional probabilities of the labels given the features. There are several strategies to do this, and we have actually talked about two such strategies in other videos. They were naive Bayes and Gaussian discriminant analysis. Those two approaches are generative. They're called generative approaches because they model the marginal distribution of the labels, and then they also model the conditional distribution of the features given the labels, making different assumptions. In naive Bayes is that everything is conditionally independent. In Gaussian discriminant analysis, it's that the conditional distributions are Gaussian. And then they apply Bayes' rule to be able to compute the conditional PMF of the labels given the observed features. Discriminative approaches take a different route, and that's the route that we're going to take today, where we attempt to estimate this conditional PMF of the labels given the features directly, without attempting to compute either the conditional distribution of the features given the labels or the PMF of the labels. Okay, so we're going to try to estimate the conditional PMF of the labels given the features without considering the others. I felt that I repeated exactly the same thing twice. Sorry about that. All right, so in logistic regression, we're going to focus on binary classification where there are just two classes, 0 and 1. In the following video, we'll talk about what do we do when we have several classes. The generalization of logistic regression to several classes is called softmax regression. But for this video, we're going to focus on just two classes. Our goal is to use a linear model to approximate the probability of one given x. Linearity is great for several reasons. One is that it's really simple and interpretable. Two is that it's usually quite effective in practice. Later on, we will talk also about how to develop nonlinear methods, both for regression and classification. But for now, we're going to try to build a model that is linear. What do we mean by a linear model? Well, we want to estimate this conditional probability of, let's say, 1 given x. I'm going to focus on the probability of the label 1 given the features x, because the probability of 0 given x, given that we're we're interested in binary classification, is just going to be 1 minus this quantity. Okay, so let's focus on the probability of one given x. We want to estimate this as a linear function of the features. Remember, in linear regression, we learn some linear coefficients and also an intercept, which is just an additive constant. We combine, we basically take an inner product between the learned fixed linear coefficients and the observed features, and then we add the additive constant, and that gives us our estimate of the response. That's linear regression. Can we do just that for classification? Well, it turns out that we cannot, because if you realize here, when the value of x changes, it is going to be very, very easy for this quantity to be larger than 1 or smaller than 0. So for most values of x, we're going to end up with something that is not a valid probability. So we cannot use this approach to directly estimate a probability from the features. The solution that we're going to apply here is to still compute a linear, well, rather affine. I'm in the math department, so maybe I should be a little bit precise about this. This is an affine function because there's an additive constant, but people call this a linear model, and that's what I'm going to do, just for clarity. So we're still going to compute a linear function of the features, but we're not going to directly interpret that as a probability. We're going to use an additional function that is going to map that to probabilities. In statistical modeling, those functions are often called link functions. The link function that we use in logistic regression is called the logistic function. That's where the name logistic regression comes from. This L here represents this, I should have defined it, this linear function of the features that is based on a fixed set of linear coefficients and an additive constant that are learned from the data. Once we have those, we plug it into this logistic function, which is of these two equivalent forms. Okay, maybe the easier form to look at is 1 over 1 plus exponential of minus L. If we plot this function, it looks like this. When L is negative and very large, then it gets mapped to 0. When L is very positive and very large, it gets mapped to 1. And in the middle, there's this transition where 0.5 corresponds to 0. The idea is that we're going to take the linear function of the features and just plug it into this function to map it onto values between 0 and 1 so that they are valid probabilities. This is called a generalized linear model because it's not really a linear model. It's like an extended linear model so that it can be used to estimate a probability. Again, we're going to learn these linear coefficients and this additive constant from the data. And then for new values of the features, we're just going to compute the linear function and then pass it through the logistic link function in order to obtain an estimate of the probability of label 1 given the observed features. That's logistic regression. It's as simple as that. So why is it a good idea to use the logistic function to do this? Well, there's different reasons. One, it's monotone. So if the linear model assigns, let's say, -4 to a certain set of features and -2 to the others, then the corresponding probabilities are going to preserve that order. The probability assigned to -2 is going to be larger than the probability assigned to -4. Okay, and this is all through the possible values of the linear combination of the features. Apart from that, it's continuous. So if we're close to here, like if we have two values that are very close in terms of the linear function, then the corresponding probabilities are also going to be very close. I should have said also that it's differentiable, which is kind of important because later on we're going to see that we want to maximize a certain likelihood function in order to learn these parameters from data, and for that it's important that the whole model be differentiable with respect to the parameters that we want to learn. Oh, this is what I was showing before. If we have two values that are very close, the linear function of the features is very close, two linear functions of features that are very close, then when we apply the logistic regression, it's going to preserve that. The corresponding probabilities are also going to be very close. And finally, it saturates. So we don't have this problem where if the features become very large, then suddenly the value explodes and cannot be interpreted as a probability. They will just get saturated into 1. So here at some point, if the features become larger and larger, they're just mapped to 1 and that's it. And the same if they become very negative, large but negative, they're just going to be mapped to 0, so we are fine. Okay, so let's talk a little bit about the lingo associated with logistic regression. The logit function is the inverse of the logistic function. So if you, just to show you what it looks like, if I rotate this to look at what the inverse looks like, that's going to be called a logit. And because of that, the input to the logistic function is usually called a logit. And this term has been preserved in the deep learning literature, as we will explain when we talk about neural networks. And that's why when you have a logistic function at the end of a neural network, the input to that logistic function is usually called a logit. Another important concept associated with the logistic regression model are the odds of the model. So the odds are the ratio between the probability of an event and the probability of the complement of the event. So for example, imagine that an event has probability 0.5, then the complement has probability also 0.5 because it's 1 minus the probability of the event. So the odds here are just 0.5 divided by 0.5, the odds are just 1. If you're familiar with betting, maybe you already know this concept, but in case you're not, that's what it means. Let's do another example, and maybe you can do this. You can pause the video and do this on your own to see if you understand. But if if the probability of an event is 0.25, then the probability of the complement is 1 minus 0.75, which is 0.25. And if we divide these two numbers, we get 3. So the odds are 3 in that case. Why am I telling you this? Because when we look at the odds for a model where the probability is produced by a logistic function, it turns out that if we plug in the logistic function here and here, because remember that in logistic regression, the logistic function gives you the probability of a 1, then when we do a little bit of math, basically we multiply by this all over the place, we see that we end up with the exponential of the input to the logistic function. This means that for a logistic regression model, if you take the logarithm of the odds, that's just an affine function of the features. So you can interpret logistic regression as if we're saying, okay, the probability cannot be a linear function of the features or an affine function of the features, but we're going to interpret the log of the odds associated with those probabilities as a linear function of the features. If you do this, then you end up with a logistic regression model. Okay, so how do we estimate the logistic regression parameters beta and alpha, or beta and alpha? I never know if I should say beta or beta. We want to estimate them from data. And what we do is we're going to model, and you won't be surprised again that we apply probabilistic modeling to this. We're going to model the ith feature vector as a random vector xi, and the label as a random variable yi. So here I should have said that this is a random vector and this is a random variable. And then we're going to maximize the conditional likelihood of the labels given the features. So up to now, we have typically maximized just the likelihood of the data that we observed in order to fit the parameters of parametric models. Here we're going to do something slightly different because we're interested in a conditional probability, as opposed to just a probability or a probability density function of the data, right? We want a conditional probability of the labels given the features. However, the idea is very, very similar. So here, the likelihood is not going to be a marginal PMF or a marginal PDF, as we had seen before when we were fitting parametric models. It's going to be a conditional PMF of the observed labels given the observed features. If you remember, when we were fitting parametric models, usually we assume that the data are IID, which means that each of the data points has the same distribution, but they're independent. And this allows us to express the likelihood as a product of each independent PMF at each data point or each independent PDF at each data point, and that enables us to actually perform estimation. Here we're going to do exactly the same thing, except that it gets a little bit trickier because we have labels and we have features. So what we're going to assume is that the labels are conditionally independent given the features. The label of example 1 is conditionally independent from the labels of the other examples if we have seen the features associated with example 1. This makes a lot of sense. I don't care what the labels are for other patients as long as I see the volume of the brain of this particular patient. Okay, so if we apply that conditional independence, then for each of the data points, I can forget about the other labels and just leave that particular label here and then multiply everything together. Okay, that's conditional independence. You can review the video on conditional independence if you don't remember. But we still have all the other features to deal with. Well, we make another very reasonable assumption, which is that we don't care about the volumes in the brains of other patients. We're only interested in this patient, and we see this patient's volumes. So if we see the features associated to YI, we don't care about the remaining features. So we can forget about the rest of the features here, and we are left with the probability of that specific label conditioned on those specific features, and we can multiply everything together because of these conditional independence assumptions. And this is the likelihood that we want to optimize in order to find alpha and beta. We want to choose the alpha and beta for which the conditional probability of the observed labels is highest given the observed features, assuming this conditional independence that the data points are not somehow interconnected. When we write that out, this is the likelihood, and this is, and I want to remind you that we parameterize these probabilities, and this is the whole point, as the logistic function of a linear function of the features. This is how we represent that model. So again, it's the logistic function of this linear function of the features. If we see, this can be a little bit tricky, so let's take a moment here. These guys can be 1 or 0, okay, because we're talking about logistic regression. So if the value is 0 for those data points, this probability is 1 minus this guy, because in logistic regression, this logistic function of the linear function of the features, I feel that I should find a more elegant way of saying that mouthful. That is an estimate of the probability of a 1, right? So if we want a probability of a 0, it has to be 1 minus that. And then for the data points that have label 1, then that is, the model estimates that probability in this way. Okay, so according to the model, this is the conditional probability of the observed labels given the observed features. Usually we operate with the logarithm of that quantity because that quantity is a lot of probabilities multiplied with each other and can be extremely small and therefore numerically unstable. So because of that, we just take the log. Since the log is a strictly increasing function or a strictly monotonic function, if we maximize this quantity, this is exactly equivalent to maximizing that quantity, and because of the logarithm, that quantity is not going to be extremely small, it's going to be easier to work with. This likelihood, in contrast to the likelihoods that we encountered when we're fitting like an exponential distribution or a Bernoulli distribution or a Gaussian distribution, have no closed form solution, but it's a concave function, which means that it looks like this, like an inverted ball. And we're going to be able to find a global maximum under certain mild conditions. And we can do this with different iterative methods. Some of the most popular ones are Newton's method or iterative reweighted least squares, which are very fast, but you can also just do gradient ascent, and that will work too. Let's take a look at an example. This is a very, very simple example where we just have one feature. For ease of visualization, usually you would have many more features. We're going to try to classify people according to their height. So this is the feature, the height. And there's two kinds of people. There's women and there's men. You can see that the men tend to be taller than women in these histograms. The white histogram is the men. The gray histogram is the women. And now we want to fit a logistic regression model to classify according to the height. So here is what the log likelihood of the model looks like. This allows us to emphasize an important point, which is that the log likelihood is a conditional probability, but it's interpreted as a function of the model parameters. Okay, that's really important. And then we want to maximize that conditional probability according to the model parameters, to choose the model parameters that enable us to discriminate between the two classes the most. So here, this function is kind of elongated in this direction, but the minimum, you can believe me, is here. Sorry, the maximum is there. Okay, we're maximizing. The maximum is there. So it kind of looks like this, and it's elongated in this direction. The maximum is there. I'm going to show you, oops, sorry about that. I'm going to show you the model corresponding to that maximum, but I'm also going to show you two other models corresponding to other values of the parameters, so you get an idea of what this maximization process is achieving. So these are the logits. This is what goes into the logistic function. These are not probabilities yet, but once they map through the logistic function, they're going to be probabilities corresponding to different values of height. This is a good thing of having a single feature. We can visualize everything very easily. And this is for the two values that are not the maximum and also for the maximum. Okay, so this line here is the one that achieves the highest likelihood. Now let's see what happens when we put these linear functions through the logistic function in order to get probability estimates. So this is for one of these two values that are not the maximum. We see that the probability estimates, which are here in the y-axis, are not amazing. Okay, there's many women for which the probability of being a man is pretty high. Okay, so these probabilities are not very discriminative between the two classes. If we look at this other value of the parameters that also does not maximize, again, it's not great because there's a fair number of men for which the probability of being a man is very small. Okay, this dotted line indicates the conditional probability of being a man given a certain height. We have arbitrarily assigned men to 1 and women to 0. And now let's take a look at the maximum value of the parameters, not of the maximum, the parameters that achieve the maximum likelihood of the model. And we obtain pretty good discrimination where most men are assigned 1 and high probability of being a man, and most women are assigned a low probability of being a man and hence a high probability of being a woman. So maximizing the likelihood enables us to get the most discriminative model of the training data. Now let's take a look at another application, which is to the diagnosis of Alzheimer's disease. Alzheimer's is a neurodegenerative disease that causes about 60 to 70 cases of dementia. It's usually diagnosed by a positron emission tomography, but this is very invasive and very costly. So there's a lot of interest in being able to estimate it using MRI, which is non-invasive and less costly. So our goal is going to be to classify patients according to features extracted from MRIs into patients that have Alzheimer's and patients that do not have Alzheimer's. The features that we're going to use are volumes of certain brain regions. One is the entorhinal cortex and the other one is the hippocampus. As an example, these are some slices of brain MRIs from cognitively normal patient. And what happens when you have Alzheimer's is that parts of your brain start shrinking. And you're going to see that because now I'm going to show you the brain of an Alzheimer's patient. And if you compare both, you see that the brain basically is shrinking, which is why this space in between here, which is called the ventricles, is becoming larger. So we've decided to use two normalized brain volumes to account for the fact that some people like me have very big heads. And those two brain regions, the volumes of the two brain regions are the volumes of the entorhinal cortex and the volumes of the hippocampus. And we see that healthy people tend to have larger hippocampus and larger entorhinal cortex. Now we want to fit a model that enables us to quantify that, assigning a conditional probability of having Alzheimer's given certain volumes of these two brain regions. In order to do that, we're going to fit a logistic regression model to the data. These are the values of the parameters. Now we have two linear coefficients because we have two features and still only one additive constant. And those are the values that maximize the likelihood over this training set. This gives you a linear model of the two features that I'm showing here, so a plane. So here, just to be clear, this is one of the features, this is another feature, and in the y-axis we have the logits. This is the linear function. That's an amazing line that I drew there. This is a linear function that is going to go into the logistic function in order to give us probabilities. Let's take a look at what happens when we do that. Boom. This is what happens. And I've plotted also, it's kind of a little bit difficult to see in 3D, but these are the patients with Alzheimer's and these are the healthy patients. And here what we obtain is this logistic curve in 3D that separates them, ideally, right? Like this is by maximizing the likelihood, we're choosing this 3D surface so that it assigns a high probability to these guys, high probability of having Alzheimer's, and a low probability to those guys. And the way we achieve that is by maximizing the likelihood of the observed data, which is the conditional probabilities of either Alzheimer's or healthy, depending on the real status of the patients, given the two brain volumes. This is maybe a better way to visualize this. Here, these are contour lines of the estimated probabilities, and realize that they're linear because they're based on a linear function of the features of the two features that then is plugged into the logistic function. And we can see that indeed it assigns low probabilities to healthy patients and then high probabilities to Alzheimer's patients when the two volumes are smaller. So it does what it should do. We discussed in the context of linear regression that sometimes for linear models, when there's feature collinearity, this produces noisy coefficients that can overfit the data. This can also happen in logistic regression, and a possible solution is the same as in linear regression, where we apply regularization. So just to show you what this would mean, we take the minus logarithm of the minus log likelihood, which typically the log likelihood, we want to maximize it, but now we're going to combine it with a regularization term that we would want to minimize. So that's why we have a minus here, so that we would want to minimize this term. And the regularization term that we're going to add basically controls the amplitudes of the coefficients in the linear model. Here we've put the L2 norm, which is analogous to rich regression, which we have seen that is very effective in controlling the coefficients and preventing overfitting in linear regression. If you wanted sparse coefficients to select just a few features with which to do classification, then you could apply the L1 norm as in the lasso. I'm not going to show you an example about this. I'll show you an example about how this works for classification in the next video on softmax regression. All right, so what have we learned? We have learned how logistic regression works. The idea is actually quite simple. You learn a linear function of the features, which are called, this linear function is called a logit, which is going to be mapped to a probability estimate by a fixed link function, which is a logistic function. We learned how to fit the model, which is basically by maximizing the likelihood of the observed data, which is the conditional probability of the different labels given the observed features. And we also, I thought there was one more, but well, we also learned about how to apply regularization to the logistic regression model. And that's all I got. Thank you very much.